I don't have any problem with people missing class for my online classes. I obviously, if you don't get a chance to even look at the videos, this is in response to one of the emails that students sent me. Uh, if you don't get a chance to watch the videos at all, and you don't get a chance to ask questions after seeing those videos, then I would say it might be very hard for you to pass my class. Uh, but at least it's 241. That makes it a little easier. And two, I'm completely willing to, spend some extra time with you, have extra office hours, meet you, at least via Zoom. I can meet you on Tuesdays, Thursdays, Fridays, give you extra time and all that sort of stuff. But no, I'm not going to drop anybody just because you weren't able to attend my Zoom meetings for any of my online classes. I actually allow you to miss as many as you want, more or less, long as you keep me informed that you are attending class or that you're in the class and you don't plan on dropping it or anything. Uh, if I don't hear from you and you skip, 3 days in a row, I'm supposed to drop you. Or if once you miss 5 days, I'm supposed to drop you. But I don't do any of that if you're actually trying to survive the class and trying to make it. So just the fact that you sent me emails asking about that is good enough to let me know that, yeah, you're not interested in dropping the class, except if you can't pass. So uh, I'm saying you can definitely still pass. You just need, like I said, if you need extra time, with me, then that's fine. Or if you just need some time to catch up, I can work with you on that. Just contact me and we'll do whatever you can. Also, don't forget in my syllabus, once you've emailed me and 2 business days as defined in that syllabus has passed, then your job is to actually send me a text message at my cell phone. As opposed to just continuing to send emails. So definitely do that because I get so many emails, it's very easy for me to miss them. And if, which I think you actually sent yours correctly, Anthony, by the way. But if, for instance, if they didn't have the PHY 241 night or whatever the subject line, then there's a good chance I would miss it anyways. So just keep that in mind. Anybody else have any other questions? And if you need to talk to me more after class, you can, Anthony, by the way. You can do it private or whatever. It doesn't matter. We can put out and breakout rooms if there's more people here with other questions. But if anybody has any other questions, feel free to ask me. Looks like we're about 2 minutes into the class period, so I should be starting in a second. The all the meetings go like I basically keep a check on how many people show up. Like as soon as you come in here, I normally ask everybody to go ahead and chat me your first and last name. That's what I use for attendance. There's ways I could actually find it. Uh, electronically without having to get you guys to do that, but I've discovered that sometimes that's a pain in the butt. So it's better if I just get you guys to chat me your first and last name. I'm not going to ever take off points for you not attending. I'm not going to think worse of you for you not attending. I get it. If someone's taking an online class, it's probably because they have some time constraints that makes it hard for them to take a regular class. So I'm certainly more than kind at letting people miss. So yeah, it's nothing harms you for attendance. Nothing necessarily makes your grade better by attendance, other than just the fact that you get to interact with the instructor more and other students, of course. So, any questions? All right, well, let's get started. You will notice that on the 17th and the 12th, I did post videos for the classes that we met. And in those classes, I covered some important things, like I did a chain of boxes where you basically have a box, rope tied to that box to the back of another box, then another box, then a rope tied to that second box and runs to a third box, and then that third box has a force pulling it. And my job or your job in solving that problem was to find out the net acceleration of the chain of boxes, but also figure out what the tensions in the ropes were. So that's very much like a problem in your book. And that's on purpose because that's one of the big things you got to figure out is what are these things that we keep calling tension. There's also various problems where I did, for instance, an inclined plane last time. I did an inclined plane with an Atwood machine. Your book just does an inclined plane for chapter 4, and it asks, more or less what makes an object slide down an incline. If you think about it, obviously the force on the object is just mg as I derived in class that weight is equal to mg. So you've got mg pushing or pulling down towards the center of the earth, but the thing is on an incline. So you're trying to look for some force that actually is parallel to the incline to push it down. And that was part of the reason that we worked with an incline when I did the Atwood machine, is so that you'd see there's a term, mg cosine theta, that more or less matches the normal force, but then there's an mg sine theta that's actually responsible for making the force that's parallel to the incline. You can also see that, for instance, I think it's episode 2 of The Big Bang Theory, where Sheldon and Leonard have to carry a piece of furniture up the steps, and they estimate that the angle of the steps was 30 degrees, and therefore the force would be mg sine theta. And he says, so we call it about half. So, that's actually a physics problem worked out. So do keep that in mind. It's kind of nice when people get their science right, which they did in Big Bang Theory there. So, anyways, that was another one. And we also have a couple problems that are coming up now that I want to show you. So that's where we're going now. I just want to remind you to look at 217 and 212. Both of those days were days in which I covered stuff from chapter 4. Today's the last day of covering chapter 4. In actuality, I've actually covered it way more than I was planning to. So y'all do have a test that's due this Sunday at 11:59 p.m. And that's an online test. You get, I think I gave you guys 3 attempts and only your highest score counts. And you have a practice test that, of course, is essentially identical to that in some sense, and you can take that as many times as you want until you take the practice test. Until you take the online test. Once you have reached the deadline for the online test, both the practice test and the face-to-face, or excuse me, the practice test and the online test will disappear. So make sure you get them done before then. So someone says, "Are we required to be here?" No, Isaiah, you're not required. This is just an opportunity for you to have office hours if you have any questions. I'll probably be posting some videos. I know you are from a different class, as is Colin and a couple other people in here. None of you are required. This is just an opportunity in case you had any last minute questions about chapter 4, or for my people in my 242 class about chapter 19 and 20. So none of you have to be here. I just wanted to let everybody know that this was here in case y'all wanted some last minute office hours. Everybody has a test due, depending on whether they meet on Mondays and Wednesdays or Tuesdays and Thursdays. But if you meet on Monday and Wednesday, your online test is due this coming Sunday. If you meet on Tuesdays and Thursdays, your online test is due this coming Monday. So make sure y'all get that done. I'm going to go ahead and share my screen, and you can see the first problem we're going to work. And this is a fairly typical type of problem, very simple, no friction. We haven't learned enough yet about friction to do anything with it. That's what we cover in chapter 5. That's one of the things we cover in chapter 5. So this one is just another look at what happens to the normal force under certain conditions. So for instance, when I did the inclined plane and Atwood machine earlier, you got to see that the normal force is not always vertical. 2, that the normal force is not always the weight. This does more of that. So it says a 15.0 kilogram box rests on a level, frictionless surface. When a person exerts a 50.0 Newton force on the box, the force is applied at 36.9 degrees above horizontal. A, what is the normal force on the box? And B, what horizontal acceleration does it experience? So that is the problem we're trying to work. You'll see there's a problem more or less just like this in your book in chapter 4. I'm trying to, do something consistent with that, but not something that violates copyright orders. So here we go, our copyright laws. So here's the solution. What we know is Newton's second law is valid. So Newton's second law tells us that the summation of all the forces acting on the object of mass m is equal to m times the acceleration, and that's a vector equation which shows us that the acceleration has to be parallel to the sum of the forces acting on the mass m. and the acceleration is inversely proportional, of course, to the mass and directly proportional to the total force. We have that. I'm going to draw a box like we're talking about here. So here's the box we're talking about. It has a mass of 15.0 kilograms. It's sitting on a frictionless surface like such. But what we do is we recognize that there's a force acting on it, and that force is acting at 36.9 degrees above horizontal, and the force is in fact 50.0 newtons. Okay. What we're asked to find in this case is the normal force, which I usually just call N, and the horizontal acceleration, which we would call a sub x. But since that's the only acceleration, we're just going to call it a. We will use F equals ma, but in this case, we're going to use the two versions of it. The two versions that are relevant: summation of forces in the x direction equals mass times acceleration in the x direction, and the summation forces in the y direction is equal to mass times acceleration in the y direction. But this is a box that's sitting on a horizontal surface that's frictionless. There's no reason to suspect that it's going to be lifted off the surface. So what's more than likely going to happen is the box is going to slide to the right, say, on the level surface, so that the position or the distance away from the level surface is not going to change. And it's still not going to change, and it's still not going to change. So that means it has no velocity, and that means since it's still not going to change, it has no acceleration. So in this case, we'll get the summation of the forces in the y direction is actually equal to zero. That will let us determine the normal force. So let's now change this diagram into a free body diagram, which we can pretty much get it from there, but I usually like to draw a coordinate system as a bare minimum. So what I'll do is I'm going to draw this coordinate system right here. This is my x-axis, that's my y-axis. I'm going to say the mass is right here, and its mass is 15.0 kilograms. The forces I have acting on it are upward, which is our positive direction, and that force is the normal force. So I'll label that N. But in the downward direction, I have the weight, which is the force due to gravity. That is the attraction of the planet to the actual mass. So in this case, it's weight is equal to mg, which is, of course, 15 times 9.80, which gives us 147.0 newtons. Notice I carried one extra sig fig just to make sure you knew that we had 3 sig figs on everything. I also have a force that has not been made into components parallel to the x and y axes. So I'm going to draw that vector black, and its magnitude is 50.0 newtons, and the angle, as I said, is 36.9 degrees. Now I can draw the x and y components. Remember, the trick to this is that once you have your vector drawn that you want them to break into components, you imagine taking a trip from the tail of the vector to the head of the vector. Tail to head. Okay? But you're not going to do it along the vector itself. You're going to do it along the components. So if I want to draw my y or my x component first, then I have to go from this spot right here to directly under the n, and you'll notice that that direction is to the right, which happens to be the positive x direction. Then I have to go from directly under it upward to the end of the vector, and in that case I'm going upward, which is the positive y direction, and that's the y component. So you see that the x component points to the right, therefore is positive. The y component points up and is therefore positive. Now, you might think, well, what if I decide to do it differently? Like, I don't want my components to be down here and there. I want them to be up here and over here, say. Well, if you do that, you're still going to have to start at the end and go to the head, and you need to do it along the y-axis first, which would be right about here, and then along the x-axis, which is right about here. Notice going along the y-axis, I had to go up, so that's a positive direction, and along the x-axis, I had to go to the right again, which is again positive. So there's no ambiguity in this process. You should be able to make out once you've decided which direction you call positive x and which direction you call positive y, and maybe even which direction you call positive z. You should be able to figure out the component signs. All right. So drawing these components on here, they're both positive. So I'm going to write a blue vector to represent f sub x being positive, and then I'm going to draw a blue vector representing f sub y as also positive, and of course the 50 newtons is what I'm calling f. Okay. So, as I warned you when we first started talking about chapter 3 in vectors, it's best to go ahead and take the time to write out what sine is and what cosine is, and then decide what your components are going to be. So if I write the sine of 36.9 degrees, sine is equal to opposite over hypotenuse. The opposite is f sub y, and the hypotenuse is 50.0 newtons. Similarly, if I write cosine of 36.9 degrees, cosine is adjacent over hypotenuse, and adjacent is f sub x, and the hypotenuse again is 50.0 newtons. So we can see that f sub x is equal to 50.0 newtons times the cosine of 36.9 degrees. Now, if you remember your trig functions and your special triangles, obviously 36.9 is the 3, 4, 5 triangle, and the 36.9 degrees is opposite the small side. So that means the adjacent side, which is our x component, is going to be the long side, and therefore cosine 36.9 is just 0.8, so we get 40.0 newtons. And remember, let me write this a little clearer. I didn't make my decimal point large enough. Let me make it clear that it is positive, and I'm writing 40.00 newtons. Again, just adding one extra digit beyond the sig figs. F sub y is also forced to be positive. This one's 50.0 newtons times the sine of 36.9 degrees. Again, the 36.9 degrees is the one that's opposite the small side, so that one should be 30. Or you can look at it as, for instance, the sine of 36.9 is 0.6. And just checking my calculator, sine of 36.9 is 0.6, which gives me, of course, positive 30.00 newtons. So now I have those forces, and all I have to do is now do my summation of forces in the x direction to find the x acceleration, and then the summation of forces in my y direction to find the normal force. I think I'll start with the summation of forces in the y direction. So the summation of forces in the y direction is equal to mass times acceleration in the y direction. As I explained to you, unless they're telling you specifically that the object you're studying will be jumping up off the table or off the level surface or digging into the level surface, then you have to just assume it's sliding along a level floor. And as long as you're sliding along a level floor, there is no velocity in the vertical direction, and therefore there is no acceleration in the vertical direction. Not because velocity equals zero means acceleration is zero, because that's not a thing. Okay. But if the velocity is zero and then you wait a couple seconds and it's still zero, that means the acceleration is zero. So I'm going to write a sub y is equal to 0. And now I'll just write this out. The forces in the y direction, I have, remember the left-hand side's always addition. So I usually take the positive ones first, which in our axes, you can see that the two positive vertical forces are the N and the Fy. So I'm going to say N plus F sub Y, which we found was 30.0 newtons positive. Both of those are in the positive y direction. That's why they have the positive sign. And then we're going to add to that this negative 147 newtons, which is the weight, and the extra uh, digit there is the zero, or the tenths digit. But now we can set all that equal to 0, and from that we see that the normal force is actually equal to, when I bring the 147 to the right-hand side, it becomes positive, and then I subtract 30 from both sides. That means 147 minus 30, therefore I get 117, so the normal force is 117.0 newtons, and again, that 0 is not a significant figure. So there's our normal force. Notice it is less than our weight. That's another trend I want you to see. When someone is pulling or pushing on a block or a box or something sitting on a level surface, if they're pushing even slightly downward, that's going to increase the normal force. If they're pushing even slightly upward, that's going to decrease the normal force. And that's what we see happen here, is the normal force decreased. Any questions on that part? All right. Again, since some people are still coming in, I want to just remind everybody that if you should go ahead and chat me your first and last name. That'll count for roll. So I just want to remind everybody that, since a bunch of people have come in since my initial start. And yes, we got that. Gotcha. Okay. So now we got to do the second part. This was part A. So I'll just put an A there. Now the second part, like I said, is where we're trying to determine the acceleration in the x direction. So again, I'm going to use the summation of the forces, but this time it's the summation of forces in the x direction is equal to mass times acceleration in the x direction. But this time that's the only acceleration that exists, so we're just going to call it A instead of subscripting it. But just like last time, we're still going to try to find all the positives and all the negatives. So in this case, if you look at our free body diagram, you can only see basically an F sub x. That's the only force acting horizontally, forward or backwards, and it happens to be positive. So it's going to be F sub x, which is positive 40.0 newtons, is equal to 15.0 kilograms times A. So from that, we get that A would be 40 divided by 15, which is 2 and 2/3. So we get 2.667. Notice we're actually dividing a newton by a kilogram. A newton is a kilogram meter per second squared. So when you divide it by a kilogram, you just get meter per second squared. But when we're talking about acceleration, we call that meters per second every second. We also had 3 sig figs divided by 3 sig figs, so that means the 7 that I put there is not a significant figure. So the acceleration would be about 2.67 meters per second every second. Again, I want to remind you that all the stuff we learned in kinematics is still fair game, so that I could now say, okay, if the horizontal surface is quite long and frictionless, I could ask you, if the box started from rest, how fast would it be going after 12.2 seconds, and how much distance would it have traveled in 12.2 seconds? So all of those other kinematic questions are still available to us, and they're going to be literally available to us until the last day of even the third semester of this course, if you happen to go somewhere where they offer a third semester. So it's not something that basically goes away. That's not the way physics and math works. Do want to remind you guys that when you're making your free body diagram, remember the first thing you're supposed to check is everything that's touching the object of mass m, whose acceleration you're trying to find, or whose net force on it you're trying to find. In other words, whatever thing's being acted on, when you're trying to identify all the forces on it, you look at everything that touches it. And then once you've counted everything that touches it and have taken a force and drawn it to represent that contact, if it actually does apply a force, once you've done that, then you have to go to the sort of magical things, what I call it action at a distance. And until we get into talking about electric fields and magnetic fields and nuclear forces, both strong and weak, the only force that acts at a distance is gravity. So right now you need to think, okay, once I've considered everything that's touching the object, I then need to think about the things that aren't touching it that could apply action at a distance, and that is gravity, the electric field, the magnetic field, the strong nuclear force, or the weak nuclear force. So just keep that in mind, and hopefully that'll keep you from missing any forces. Anybody have any questions on that one? Okay, so that was a pretty major type of problem that I wanted to make sure you guys had seen. Again, it's a little bit about the normal force and how that changes, but it's also about breaking vectors up into components and stuff of that sort. So I wanted to make sure you guys could do that. There's another one that's quite good that involves pulleys, so I want to do a problem like that. So this will be called example two. And in this example, what we're going to imagine is, let's just imagine someone's trying to lift something up on top of a high roof, say. They actually set up a system where they have sort of like a crane boom that hangs out from the roof out over the edge. And what can be done there is you can, for instance, tie a rope to one end, have it run down, go around a pulley like this, and then come back up and then run into another pulley that's connected like that. And this time the person could apply force FT, which I would normally call T, but I'm going to call it FT this time. It's a tension force. Okay. So you could imagine a person standing there on the roof and they're pulling that rope uh, horizontally or sort of diagonally like that. And it's all in an attempt to lift this object of mass M. Okay. So what we want to know is if M equals, let's say, 1700.0 kilograms, and all right, say if M equals 1700 kilograms, what is the minimum force FT that can be applied to the rope to barely accelerate the mass. In other words, I want the acceleration to not be zero, but I just want to know basically that it's going to be slightly bigger than zero. Therefore, I'll get a force that has to be slightly bigger than something. So we're trying to figure out what that minimum force is going to be. So, So again, I'm going to draw a free body diagram and I'm going to explain to you how we have to treat tensions in ropes. So when you apply a force to a rope, that's called a tension. And there's very specific ways you can do it. For instance, if this were a rope, which is clearly not, it's a solid object, but if it were a rope and I tried to push it this way against something, it would just roll up. So that's the key thing about ropes is you can't apply uh, a force along it except in tension. So you can pull on it, but you can never push on it. So when you do apply a force of tension on a rope, what happens is that tension will distribute itself and be exactly the same on every part of the rope unless the rope has mass. Because once it has mass, then the tension has to be a little different. Because, for instance, if you're pulling it from the very end, you have to pull the thing at the end of the rope plus all the rope. Whereas if you go halfway from the end of the rope toward the thing that's tied to the other end of the rope, then you only have to pull the thing at the end of the rope and half the mass of the rope. So that's where the mass of the rope comes in. It actually makes you have to apply more force depending on how much rope you got to move. So in this case, we're going to assume the rope is actually massless, and therefore the tension is going to be the same everywhere. Now I can draw a free body diagram. My free body diagram is going to include uh, an X and Y axis, but to be honest, you only really need the Y axis. So I'm going to say the Y axis is pointing up. I'm going to represent the mass M, which equals 1,700 kilograms by that little red dot. Now, here's the tricky part. What you see is this part of the rope is going to be pulling up on it, and this part of the rope is also going to be pulling up on it. That's what this pulley allows to happen, just like this pulley allows this force to become this force, which is, of course, the same as that force. And if you were to be riding along this, let's say standing on that mass M as it went up, what you would notice is uh, clearly this rope is lifting you up, but you'd also have to conclude that this rope is also lifting you up. Because of that, we have to reach the conclusion that we have, in fact, two forces acting in the upward direction. Ft, and then another one that's equal in magnitude. So it's also called Ft. But then we have a negative force acting as well, and that negative force is the weight, which equals mg. And of course, that's kind of a big deal because it's 1,700 times 9.8. That gives me 16,660 newtons, but we really only had 4 sig figs, so that ones place is not a significant digit. Only the tens, the hundreds, the thousands, and the 10,000s are sig figs. Now that I have that, I can go ahead and write out my solution. I actually probably should have written out solution before I drew the free body diagram, but either way, it's cool. We are using, of course, the summation forces, in this case, in the y direction is equal to mass times acceleration in the y direction. And we used, of course, weight is equal to mg. Luckily, all these forces are parallel or anti-parallel to the positive y-axis, so we don't really have to break any components down. But the left-hand side of Newton's second law therefore becomes Ft plus Ft plus negative 16,660 newtons. And in this case, what we want is the acceleration to be slightly bigger than zero. So if we multiply m times zero, we'd get zero. So I'm going to say less than or equal to zero would give me an acceleration equal to zero. So I'm just going to say less than zero like that. So instead of putting equals ma, I'm going to say is less than zero. Okay, meaning zero. Well, no, I don't want to. I want it to be bigger than zero, I guess would be a better way of saying it. Yeah, yeah, that's it. Sorry about that. Remember, what I want is just barely big enough to accelerate it. So we could call the acceleration zero if you want it, and that's sort of what I'm doing here. So I'm going to write greater than zero is what the acceleration has to be, and that'll just allow us to solve for ft, and it'll say something like ft is greater than something. Okay, so we can combine the two like terms. We obviously get 2ft minus 16,660 newtons is greater than zero. And of course, we can then solve for ft and see that ft, I wrote equals for a second there, but we see that ft is going to be greater than 16,660 newtons divided by 2. So when we divide that by 2, it's pretty obvious that it's going to be 8,330. So we see that the ft is greater than, if we actually had it equal to, then the acceleration would be exactly zero. So I'm just going to say it's greater than 8,000. Oh, darn it, I hate it when it happens. Greater than 8,330 newtons. Notice that is 4 sig fig, so all of those are significant, and that's the answer. So basically, what we discovered is when we have a pulley set up in such a way that you have two ropes that potentially pull it up, then you're multiplying the force by a factor of two. Now, the disadvantage is this. If I'm up at the top of the roof and I pull the rope 1 meter, then basically 1 meter of rope is going to go around the pulley, and that's going to cause this mast to only move up half a meter because part of it lifts half and the other half lifts half of it. So it ends up going exactly the same factor less in distance. And that's because we'll later learn there's a concept of energy and power, and the best case scenario with any machine is that it's 100% efficient, and it pretty much never is 100% efficient. And in order for it to be 100% efficient, that means the force times the distance has to equal the force times the distance on both sides. So by me putting in half as big a force on the tension, then that means I'm going to carry it twice as far. So the disadvantage is I gotta instead of lifting the thing up, let's say one, two, three, four, five, six blocks as shown on this paper. In reality, I've got to move the rope 12 blocks to make the object go up to a height of 6 blocks. Okay. Any questions on that? Okay. You'll also see there's other ways you can attach pulleys. In fact, I just saw something on Facebook today where they had multiple block and tackles set up. You can set it up so that you have many, many, many different varieties. I highly recommend you look at that. And then it's just a matter of counting the number of lines. In fact, the one that I saw online today had 6 individual lines. So that actually is allowed to bring your force down by a factor of 6. So, for instance, if you had to lift something 6,000 pounds, you could do it with just 1,000. Again, that causes the same problem though. If you had to lift it, for instance, 100 feet, now you're going to have to lift it 600 feet. But again, 600 feet is doable. That's just a tiresome thing. Whereas 6,000 pounds might not be able to lift by yourself anyway. So you were able to accomplish a 6,000 pound lift, and the cost being that you'd have to carry it 6 times as far. Any questions on that one? All right. There's another problem. Actually, let me start with this one first. This one's kind of a fun little problem. And the main reason I'm showing you this one is sort of the same reason that I showed you the Atwood machine 2 different ways. Specifically, it gives us another technique of solving systems of equations that you probably were never taught in your let's say your high school algebra 1, high school algebra 2 class. You didn't learn it in your trig class. You didn't learn it uh, in your pre-calculus class or anything like that. This is one way that we often use in physics that you pretty much never learn about in math. So I just want to show you that. What we have here is what I call the fuzzy dice problem. So let's call this example three. Uh, example three. A symmetric pair of fuzzy dice hanging from a rear view mirror can be used as an accelerometer. Find expressions or find, let's write it this way. I'll say find equations to find the tension in the ropes holding the dice and an equation for the acceleration of the car and its dependence on theta. Okay. So I'll draw the picture and that'll further explain this to some extent, hopefully, anyways. So the picture we're looking at right here is you imagine a little rearview mirror. Maybe it's sort of looking like this is your rearview mirror. It's coming off your windshield, something like this. Okay. What I'm going to imagine is tying a string, and I had to make this symmetric fuzzy dice because it turns out if you hang something that is oddly shaped, like if I hung some something that was shaped like this, it had weight that looks like it would be distributed like this weight is. If I hung it, it would not hang flat. In fact, like if I tied a string right here, what would happen is this thing would probably end up hanging something like this with the rope like that, and therefore the rope wouldn't even necessarily be level. It would probably be at some angle like that. So that's why I had to say it's symmetric, because if you actually use something that's not symmetric, you'd get an angle that wouldn't be hanging, or a string that wouldn't be hanging vertically. So in this case, what we're going to do is just picture it almost like a sinker that you might use uh, in fishing. Okay. I just realized it looks like something that a lot of people in my neighborhood hang from their rear trailer hitches. So let's best not think of that. Let's say it has a mass M, but it is symmetric. Of course, a plumb bob is a good example. You can actually go to Home Depot and they sell plumb bobs. This is what you use to find what we call plumb, which is verticalness. And basically, it is a symmetric shape that is cylindrical, so that if you rotate it about any axis through the center, it looks identical from every angle. So this would be what a plumb bob looks like. So you can see how symmetric that is. Uh, and of course, the rope would come straight out the end, so it would be purely symmetric. Now, what's going to happen is when we actually accelerate the car, so we hit the accelerator, uh, what's going to happen is the string cannot provide a force except a tension upward. It can't provide a leftward force or a rightward force, nor can it provide a uh, downward force. It can't push down because it can only, work in tension. But once the car takes off to the right rapidly, what's going to happen is the string is going to move out an angle theta. And we'll just imagine as if it's a little point mass on the end here. And therefore, we have a force that's equal to the weight uh, of it hanging downward. Okay. So, what I want to do is figure out how uh, define the tension T in the string, as well as assuming we know M and theta, as well as the acceleration that the car would have if it made an angle theta. So here we go. Our solution again is going to involve Newton's second law. In this case, we're going to have to do it in the x and y direction. So the summation of the forces in the x direction equals mass times acceleration in the x direction. And the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now I'm going to draw a free body diagram to make this a little bit more easy to understand. So let me draw a little coordinate axis like this. Okay, here's my x-axis, there's my y-axis, and the mass is going to be right here at the origin, and the rope will go up at an angle theta with the vertical. So this angle is theta, but more specifically, we know we have a force that's the tension in the rope, and that force is going to act this way. That force is neither parallel to the x-axis or the y-axis, so I needed to draw it black, and I'm calling it T for tension. Now, we do have a force that's a weight, and that actually acts downward, which is parallel to the negative y-axis. So it's okay to go ahead and draw that as red, because the red is the color I've been using for negative forces, forces pointing in the negative direction, in other words. And that, of course, is the weight, which equals m times g. Okay, so again, we're pretending we know m, we pretend we know g, and we pretend we know theta. And what we want to find is A and the T, the tension in it. Uh, that's what we have to find. So we'll say, going back to purple here, we'll say A equals question mark, and we'll say T equals question mark. Okay. So we can go ahead and break this up into components in the x and y directions. And this tension, of course, would have an x component pointing this way. I'd call that T sub x. And by now you can probably see, since the theta is up there, you can probably see that Tx is going to be T times the sine of theta. If not, just take the time and write sine out and then write cosine. We also are going to have a upwardly directed y component, and that one is T sub y. And again, this case is going to be T cosine theta. So notice this is an instance where the x actually was given by sine, not cosine, and the y was given by cosine, not sine. That's why I want you to do this every time and work out exactly which trig function it is. Don't always assume it's, cosine for x and sine for y. Now I can take the summation of forces in the y direction is equal to mass times acceleration in the y direction. But what's going to happen here is when the person takes off, before they take off, the string will be hanging straight down with the dice below it. But once he takes off, if he's able to hold a constant acceleration for, a couple seconds, say, then while he's accelerating up to that, or while he's jerking up to that max acceleration that he's going to have, it switches from hanging straight down to hanging like this. And if he's able to hold a constant acceleration for any period of time, then this angle should stay exactly that. Now, in principle, it could go a little too far and then it's going to swing back and forth, but we're imagining that we've already let that play out and now it's at this static angle theta while the car is accelerating at this accelerated rate A that we want to determine what it is in terms of theta. Okay. So, and when it's like this means yes, this thing is still moving to the right, but it's not moving up and down. So the acceleration in the y direction is actually going to be zero. Okay. So that gives us this expression. The left-hand side, the only force in the y direction that's positive is the ty. So I'm going to write down t cosine theta. And then the only force acting in the negative direction is the negative mg. So I'm going to write plus negative mg. And then all that is equal to zero. Now, it turns out that this will be super helpful if I just put the mg on the other side. So I'm going to do that. T cosine theta is equal to mg, and I'm going to call that equation 1. Now, the other thing I'm going to do over in this corner, the summation forces in the x direction equals mass times acceleration in the x direction. Only this time, the only acceleration is a sub x, so we're just going to call it a. And in this case, we only have one force acting, and that's t times the sine of theta. It's acting in the positive direction, so we're going to say t sine theta is equal to m times a, and we'll call that equation 2. So here comes the part that I did this for specifically. Remember, I told you I'm teaching you a way to solve a system of equations that you might not have seen before. The way here is I am going to divide equation 2 by 1. So divide 2 by 1. When you do that, I think you'll see that you get t sine theta over t cosine theta, which obviously the t's cancel out, and it's just going to give you sine theta over cosine theta, which is tangent theta. But the right-hand side is going to be m times a over m times g. So the m's are going to cancel out as well, and you end up getting, therefore, I hate it when it does that. You end up getting, therefore, that a is equal to g times the tangent of theta, and that's just making use of the trig identity that sine over cosine is tangent. Everybody sees how I got that? Any questions? All right. So now that we know A, in principle, we can plug A back into, uh, let's say, equation 2 and then solve for sine. If we did that, then we'd get, or excuse me, and then solve for t. If we did that, we'd get t equals ma over sine theta. That's mg tangent theta over sine theta, which is mg cosine theta over sine squared theta. So t is equal to mg. Remember, tangent theta is sine over cosine. Oh, it's even better than I thought. Sorry, I was picturing the tangent upside down. Since we had a tangent theta on top, the tangent is sine over cosine. We're now taking that m times a tangent theta and we're dividing it by sine theta. So the sine theta over cosine theta divided by sine theta just becomes 1 over cosine theta, and that is our answer. So If you know theta and m and g, you can tell that the tension in the rope is just going to be mg over cosine theta. So the big trick there was we divided one equation by another. Hopefully, y'all have seen that before, but if you haven't, just remember the reason why we don't do this in math is there's that big problem. You can, quote unquote, add anything to both sides of an equation, long as you do it, whatever you do to one side, you do to the other. You can also multiply each side of an equation by any number you want to, as long as whatever you do to one side, you do to the other. But there is a caveat. You're not supposed to multiply by zero on both sides, and you're certainly never supposed to divide by zero anywhere, period. Okay. So that's the danger of dividing one equation by another. You could be inadvertently dividing by zero. In this case, we know we're not dealing with a situation in which either of these are relevant when the values are zero. So it's certainly fine to divide by them, at least for these physical cases. So, anybody have any questions on that? Okay, so that's pretty much the last major problem that I wanted to make sure I got done for you guys. Uh, you can look at the other problems in the book. For instance, there was one where there's a boat being pulled by two cords. I wish they would go further and actually uh, then give you the mass of the boat and then ask you to solve for the acceleration of the boat. I don't know why they didn't do that, but they did do the other part, which was making sure that you could add the forces, break them down into components, and then add them appropriately. So make sure you can do that. I did that one actually in my face-to-face class. I chose not to do it online, but if you want to, you can still, get me to show you that in an office hour or anything like that. But definitely at least look it up and how they did it in your book and know that. So this basically kills and finishes chapter 4. I'm going to go a little bit into chapter 5 now. Anybody have any questions? Okay. So one of the ways I tend to start chapter 5, which by the way is called using Newton's laws of motion. Uh, I think that's what it's called. Using Newton's laws, friction, circular motion, and drag forces. So this chapter, chapter 5, is going to introduce some other things. So I'm going to start off by introducing those to you so that you'll have some idea what they actually are. So what we have is chapter 5. Again, make sure you ask me if I'm talking too fast or going over this stuff too fast. Make sure you ask me to stop and explain something if you don't understand it. But chapter 5, like I said, is friction, centripetal force, or circular motion, circular motion, and drag forces. So drag forces are the forces we get due to air resistance, basically. They call that air drag or drag force or something like that. That's basically what we're talking about here. So first off, I want to tell you if you take something simple like a calculator, especially if your calculator has those little somewhat tacky rubber toes or feet or whatever they're like little nipples that are on the bottom and they can be like rubber or silicone or something like that and if they're kind of tacky that actually helps because it makes them a little bit more friction full. But what I would like you to do when thinking about this is I'd like you to take a calculator or something of some weight so it's not just infinitely easy to push it but something of some weight with some grip on a level surface. And what you'll notice is if I push, now I'm imagining this, or you should be imagining this sitting on my desk, but me pushing just ever so slightly with like a 1/1000th of a Newton force. And what you'll see is it doesn't move. And then I'll go to 2/1000th of a force and it doesn't move either. And I'll go to 3/1000ths of a Newton and it doesn't move either. In fact, I can keep doing that. And what we're discovering is there's a friction called the static friction, because notice, again, imagining this sitting on a desk, there's no motion of the calculator relative to the desk. Therefore, it's in what we call a static situation where there's no relative motion. That friction is called static friction, and it turns out to be the stronger, more important one. So, what I want you to understand is that it has a whole litany of values it can have. For instance, I just showed you 1/1000th of a Newton, 2/1000ths of a Newton, 3/1000ths of a Newton, 4/1000ths of a Newton, and I can keep on doing that, and it's always going to stop it up until I get to some maximum value at which it can't stop it. So, that tells us exactly what the friction force equation should be. I use this fancy script F for friction, and then I put a subscript S on it for static. And what we say is it is less than, oops, sorry about that. It just all of a sudden started making something different. So it's less than or equal to mu static times the normal force. So I can write it like that, because I usually write the normal force. I have actually been quite a lot lately writing F sub n. Either one of those is acceptable. So you could say R F sub S is less than or equal to mu sub S times F normal. That is it. This number right here is something we can experimentally determine, and it's called the static coefficient of friction. And lo and behold, this one is the normal force, and that's the whole reason we introduced the normal force, or that's one of the many reasons we introduced the normal force in the last chapter, because you have to be able to calculate it to use friction. Now, if you continue on with that thought experiment where you're imagining me, or hopefully you're doing it yourself with your own whatever you have at your house, but if you imagine me pushing on this with 2/1000th of a Newton, 3/1000th of a Newton, 4/1000ths, I even get up to hundredths of a Newton, I then get up to whole Newtons, and all of a sudden it breaks loose at, let's say, 3 Newtons. Well, what that means is, evidently, if I took the mass of this in kilograms, and since the surface is level, the normal force is just going to be the weight, but in the opposite direction. So I'm just going to take the mass in kilograms, multiply it by 9.8. That'll give me its weight in newtons. We know, since I'm pushing exactly horizontally, I'm not pushing downward any, I'm not pushing upward any. So I'm not changing the normal force from being exactly equal in magnitude to the weight. Uh, but it turns out that the coefficient of static friction times this weight, and therefore this normal force, has to be equal to the 3 Newtons that I said I finally was able to break it. So if I kept going up and up and up, getting larger and larger friction forces, and it finally moved at 3 Newtons, then that means the mu static times the friction normal force was just smaller than 3 Newtons. Maybe it's 2.99 Newtons or something like that. Okay. So that's how that works. But the other part is, once you get that moving, what you'll see is it moves really, really easy once it's moving. That's what I want you to experience by trying to push your own calculator across the desk. Is it takes a little bit of force to get it going, but once it goes, it takes a lot less force to keep it going. And because of that, I have another equation. In this case, it's the kinetic friction is equal to mu kinetic times the normal force, or the kinetic friction. Again, the word I'm saying here is kinetic friction is equal to mu kinetic times the normal force. Okay. This is the kinetic coefficient of friction. So that one just has a simple formula where it's equal to mu k times Fn. Your book actually, in when it talks about the friction section, which is the very first section, 5.1, it actually has a table of friction coefficients for various wood surfaces, or excuse me, various surfaces of contact. So, for instance, wood on wood has a static coefficient of friction of 0.4, but a kinetic coefficient of friction of 0.2. Ice on ice, so like an ice cube sliding across a perfectly frozen smooth road, would have a static coefficient of friction of about 0.1. Notice it's a unitless number, but a kinetic coefficient of friction of 0.03. Metal on metal is 0.07 and zero point 0.1 for static. Rubber on dry concrete is zero point 0.8 for static and zero point 0.8 for kinetic. Rubber on wet concrete is zero point 0.7 for static and zero point 0.5 for rubber. So that those are all really good values to use, and that's part of the reason that your author gave you the table 5.1 in the textbook specifically so that you could use it for any kind of problems he does. So, for instance, if he asks you to solve a problem where a car is driving on wet concrete, then you can go up and look and say, "Oh, well, I have rubber on wet concrete, so I can use those coefficients of friction." Okay. So that's one thing we want to know. The circular motion part I find really, really interesting in the derivation process. So I usually get my students to derive it and that sort of thing. What I will do in this case, I'm going to go ahead and give you something to think about. So what I'm going to do is I'm going to make a vector field. Okay, remember a vector field is basically assigning to points in space various vector quantities. So you'd imagine taking every point in 3 or 4 or two-dimensional space and assigning to it exactly one vector. Okay, and then you go to another point, you assign another vector. Well, you can do that with equations. And in this case, I'm going to say the position vector is equal to r vector. And I'm going to say that r vector is in fact equal to r cosine theta I hat plus r sine theta j hat. But more specifically, I'm going to make it a function of time because I'm going to say theta is equal to some omega times t, where omega is called the angular frequency. Oops. It's called the angular frequency, or the angular velocity. Now, I could tell you that omega specifically would have units of radians per second, but I could also tell you that omega is equal to 2 pi divided by t, where t is the period of circular motion. Okay, so let me break this up a little bit from what we were doing before. So what I would like you guys to do is draw this position vector at various times. So I would like you to make a timetable. Actually, I got to change that. Let's undo this. Okay, so we're going to say t in seconds, or actually, let's not do t in seconds. Let's do t in units of periods. So I'm just going to write t, and then I'm going to write theta, and then I'm going to write r cosine theta, which is x, and I'm going to write r sine theta, which is y. Okay. And what I would like you to do is take 0, which gives me, of course, 0. And then, of course, you can figure out that when I put in theta equals 0, the cosine of theta of 0 is 1. So that's just r here. But the sine of 0 is 0. So that would be 0. And then you're going to say t over 8. And then you're going to say t over 4. Then 3t over 8. Then t over 2. Then let's say 5t over 8. Then 6t over 8 would be 3t over 4. Then 7t over 8. And then t. Now, what your job will be is I want you, actually, let's make that a little cleaner. Let me let the program draw this straight for me. What we're going to do is we're going to form an x-axis. Remember, this value, the third column is actually x, and the fourth column is actually y. So we've got one data point we've already drawn. I'm going to say 1, 2, 3, 4 is what I call r. So this distance right here is r. Okay, that's supposed to be 4 whole squares there. So we've got that. And this is t equals 0. Okay. What I want you to do is fill out this table and then continue filling out all the dots that it's going to make around on this graph. Okay. In other words, as you go ahead and choose, since theta equals omega times t, and omega is equal to 2 pi over t, then you can go ahead and fill in this column as well. So you're going to fill in this column, and then you'll use that to evaluate cosine and put it there, and you'll use it to evaluate sine, and you'll put it there. And then what you'll see is you'll ultimately get a circle. Okay, I'm trying to be a little secretive about this because I want you to discover it yourself. So you're going to plot a bunch of dots, and they're going to make some kind of circle in some kind of way. Hopefully you already know, but if you don't, that's okay. It's not a big deal. Then what I want you to do is remember that remember D is dr dt. In other words, since r is our position vector, then the velocity vector would be dr dt. So all you have to do is substitute the t into that expression, r times cosine of 2 pi over big T times little t. And in fact, let me go ahead and write it this way for you so y'all won't get confused later. I'm going to say r times cosine 2 pi over t times t I hat, like that, plus r sine 2 pi over t times t j hat. Okay. Now you can also take the derivative of the velocity, and that gives us a is equal to dv dt. So if you take the derivative of the velocity, you get the acceleration. And I want you to last part of it, let's do then calculate each of the following, which is going to be this as well as the magnitude of v of t, and this as well as the magnitude of a of t. Okay, so in other words, we're going to use the Pythagorean theorem because it's in x and y. So if you take the square root of the sum of the squares of x, which obviously is equal to r cosine theta, and the square of y, which is obviously equal to r sine theta, if you square those two and then take the square root and make, use certain identities, you'll immediately discover something very interesting about the velocity and something very interesting about the acceleration. And hopefully you can plot all the points of r for those different times. And I suspect you might even be able to figure out what the velocity vectors look like and what the acceleration vectors look like, as well as the magnitudes. So I want you guys to give that a try in the intervening period between now and our next meeting, because I'm going to come up and do this the very first thing in our first class of next week. Now, in addition to that, I want to introduce one more thing. It turns out that, yeah, we got 5 minutes. It turns out that drag forces, or excuse me, are air resistance usually acts two ways. F is equal to some constant times V, or F is equal to some constant times V squared. Okay. Uh, that's basically really all you need to do. Now, if we imagine a particle of mass M falling, but not free fall. Okay, we're actually, in this case, we're talking about falling with air resistance. So I'm going to call this the up direction, and I'm going to call this the x direction. The forces we have acting on it are the object's weight, which equals W equals mg, but we also have a force acting this way that, in this case, I'm going to say F has a magnitude equal to B times V. The V squared one we can use, but I'm not really going to test you on that or anything. So I just want to let you know that that is the case. And I would say that's more relevant if you're talking about really high speeds, or if you're going through stuff that's very thick. Like if you wanted to know what the water resistance of a submarine going through a sub was, I would suspect it'd be closer to F equals some constant times the velocity squared for a submarine, where it are for a car going, 70 miles per hour, or a truck going 70 miles per hour, it'd be more likely to be B times V squared. But with a ball in free fall, it might be more reasonable to say B times V. So that's what we're working out here. Uh, Now I can take Newton's second law. The summation of the forces in the y direction equals mass times acceleration in the y direction. Only this time the acceleration is not going to be a constant. So it's actually going to be given by a differential equation. So we'll say the summation of the forces in the y direction is equal to m times dv dt. So that's dv in the y direction. Okay. So now I can say that we have mg plus negative bv is equal to m dv dt. Now that's the only velocity we're dealing with is in the y direction, so I don't need to subscript it y anymore. What I will do is divide both sides by m. So I'm going to just write down 1 over m times 1 over m. And when I do that, I get g minus b over m times v is equal to dv dt. Now I can, going back to black, sorry about that. Now I can write dv over g minus b over mv is equal to just dt. Now, what I do when I get this point is I integrate both sides. And in so doing, I'm going to integrate from v0 equals 0 to v of t. And on this side, I'm going to integrate from t0 equals 0 to t. When I do that, you can see that I have to do some substitution on the left-hand side. So I'll write over here, left-hand side, let g minus b over m equal w, then dw is negative b over m dv. So what I have to do is multiply both sides by negative b over m. So I'm going to, or actually I could multiply it by negative, yeah, I'll do that. I'll multiply both sides by negative b over m. And now my integral becomes the integral of d omega over omega is equal to negative b over m integral dt. This is straightforward. We end up getting the natural log of w is equal to negative b over m times t. And now we resubstitute what w was supposed to be. So it's the ln of g minus b over m times v is equal to negative b over m to the t. What I'm going to do is raise, I'm going to take e and raise it to the left-hand side power, and I'm going to take e and raise it to the right-hand side power, and set them equal to each other. Of course, e to the ln of anything is just the argument of the ln, so the left-hand side becomes g minus b over m times v, and the right-hand side becomes e to the negative b over mt, like that. Now we can basically, yeah, I think what I can do is I can pull, I feel like there should be a G here somewhere. I don't think I lost it, but anyways, we'll pull the B and over M and the V to the other side, and I'm going to say G minus E to the negative B over MT is equal to B over M times V. Now I can multiply through by M over B. So I'll do this, M over B, but obviously I got to do it to both sides, M over B. And when I do that, I end up getting V of T, which is what the right-hand side is going to be equal to now, is equal to mg over B minus m over b e to the negative b over m times t. Now you can see we've got a common factor of, I don't know where my G went. The G went somewhere. I know it had to. Mg minus BV, that looks good. B over M, B over M, multiplied by M, that'd be G, that'd B over M. Yeah, everything looks fine. Anyways, so what's bothering me is when I factor out this M over B, it's like G has the same units of E. So I really think there's supposed to be a G in here somewhere that I might have lost. But the main thing is what you see here is as T approaches infinity, V of T approaches a terminal velocity, and that terminal velocity is given by V terminal is equal to mg over b. Uh, yes, mg over b. Okay, and that's the single most important part of this result is that. But what you'd see if you actually graph this is it would asymptotically approach this value, mg over b. That's the velocity as a function of time. But that's it. You guys are free to go. I'm sorry I ran 2 minutes over. Uh, of course, you're always free to go if I run over like that. But just in case, make sure you sent me or you chatted me your first and last name. I'll wait here till the last person leaves in case anybody has any questions. I will be having another one tomorrow at 5:20 to 6:40, and that'll be the last one for the week. Stay safe, stay warm, have a good time, enjoy your snow day, and thanks for coming.
Have a good night, Professor.
What's up, Aruz?
Oh,
You
good
love it?
night.
Did you like that one? Was that a little more easy understanding of the uh, terminal velocity stuff from last semester?
A little bit, but I call this. I need to reread chapter 5 to understand it more, but I can see
Yeah.
it.
Yeah, that's a little bit. I swear I think I lost a G in here somewhere, but I don't know. I have to figure out what that is, but we'll deal with it.
Okay. I'm
Thanks for
worried
coming,
about the
bud.
test next week, so
Yeah, I suspect you're going to do well. Just keep working make sure you get your homeworks and start doing the practice
yes,
tests. I think you'll be good
yes.
to go. All
I have
right.
to do my homework. That's it.
Yes.
Oh, okay.
Well, have a good
Good
one,
night.
Aries.
You too, you too. See you.
Bye
Bye.
bye. So, looks like we got that. So, just looking back at this equation just to see if I actually did miss a G, it appears to me that BV obviously is going to have units of newtons, which obviously that should have said that too. So when I divided by M on both sides, I got G minus B over M. Maybe I should have divided by MG on both sides. That might have been a little better, but either way, I could factor out a M over B times parenthesis G minus E to the negative B or T, and then you took the limit as T approaches infinity. This would become zero, so you just get M over B times G, which does give the right terminal velocity. So I guess it works. It just feels to me like G should not be added to a pure E because an E can't have any units. I just don't know where my units went. Oh well, that's it. Stop sharing, and now I'll say bye to you folks. See you later. Bye bye.